I'm doing is wind power forecasting in the short term. In the short term means 30 minutes in advance. So in order to forecast wind power, I needed to develop an algorithm to have the minimum error of prediction. And my algorithm consists of three main methods. The first one is fuzzy inference structure, neural network, and finally particle swarm optimization. So basically, when I combine all the fuzzy inference structure and neural networks, I get a root mean square error of 1.8. After adding the particle swarm optimization, which just keeps on finding the optimal value for the error, which it just minimizes the error of prediction, we get a much better error of 0.65. So basically, after adding the particle swarm optimization algorithm, we get an improvement of the error of 63%, which is awesome.
So for this project, we worked under Professor Lipson, and we were fabricating different devices called waveguides, which are essentially geometrical devices on wafers that can guide light wherever you want it to go based on geometry. So there are these things called ring resonators, which are effectively optical bandpass filters that we use to determine the Q factor of these specific ring resonators, which is essentially just the peakiness of the filtering. So we're testing different fabrication techniques to improve the Q factor of these optical ring resonators. For instance, we're trying different etching techniques and different oxidation techniques to improve the roughness of the sidewalls of these waveguides, because one of the biggest issues in optical waveguides is the roughness of the sidewalls, because once the light goes through this waveguide, it'll see the rough sidewall and become distorted. So if we can improve the roughness, then all the better. We found that if we use the improved edge, which was different than the standard edge that is currently used in the lab, we could drastically improve the Q factor by a factor of 2 or 3. However, the use of oxidation techniques was inconclusive, and it's something that we would like to look into later. In the future, we'd like to use high Q factor ring resonators with this improved edge to try to improve the Q factor of these ring resonators.
Our project is face recognition, so it's your personal visual business card using face recognition. And we have, so we're using a face recognition algorithm called LBPH, which is a local binary pattern histogram algorithm. And we're using OpenCV's face recognizer class. So the Node.js acts as a server, a face recognition server. So because we chose Node.js because it scales really good, and we're having 10 servers running at the same time. So we're having 10 servers in one computer, running at the same time. It works really cool. In that we have a face recognition app. So this is our OWS app we designed, and it's really simple. We just kind of add a face. So if you see the screen, we just have I see myself. I just add a few pictures of myself. And okay. So we have a recognition process. So during the adding phase, we train the data to know it's me. And then we have a recognition process where you should get my name. Yes, it got my name. If I tap on it, it has my name, and then it also has like some tracking ability. Yes, and it kind of tracks my name too. Follows me, kind of.